Hello, this is Dr. E again. We're covering Unit 4.5, AP Unit 4.5 on global wind patterns. The learning objective here is to explain how environmental factors can result in atmospheric circulation. The suggested skills to explain relationships between different characteristics of environmental concept, processes, and models represented visually. For example, atmospheric circulation is all about getting the energy from the sun, the density properties of air, and rotation of the Earth, which leads to the Coriolis Effect, something that is a little bit difficult to understand, but we get through it. So basically what we're looking at is air properties. First thing is that warm air rises. So as it heats up, and where's the hottest spot? Oh, the equator. And therefore at the equator, it rises. And as it rises, remember that because it's going so, the molecules are moving so fast, it holds a lot more moisture. However, as it rises, it gets colder because it's rising, and therefore it's going to rain. That's why we have the rainforest at 0 degrees at the equator. Now, once it gets up very, very high, it has no place to go. It can't go up any farther, and so it's going to go north. Half of it's going to go south, but it has very little moisture in it. Eventually, it's going to come back down. And when it comes back down, it's going to start getting warmer and warmer and warmer. And as it does, there's no moisture left to rain out. So at 30 degrees north and 30 degrees south, there are deserts. For example, the Sahara or Southern California. The thing here is because the air is coming down, there's high pressures becoming more dense. At 0 degrees, it's low pressure. Why? Because the air is leaving, so it's low pressure. And therefore, the air is going to go from high pressure to low pressure. Now, the Coriolis effect is caused because if I'm standing at the exact North Pole, I'm spinning around once every 24 hours. I'm not going very fast. Whereas at the equator, it's rotating very, very rapidly. So there's a difference. And so if I throw a baseball here, the ball is going to be going what it thought was a straight line. But it turns out to be, because the Earth is spinning, it's going to be deflected to the right in the north and the left in the south hemisphere. So deflections of objects traveling through atmosphere due to the spin of the Earth. Now the next thing you need to remember is that air at 30 degrees moves back to lower pressure at the atmosphere. And so it comes up here and it's going to move south. And it's going to be moving towards the left. Winds 0 to 30 degrees go from east to west because the Earth is spinning this direction, and therefore air can't keep up with the Earth's, and therefore it's going to be moving this direction. Between 30 and 60, however, it moves from the west to the east because the Earth spins faster at 30 degrees than 60 degrees. Now the global wind patterns, air moves from 30 to 0 and from 30 to 60. Why? Because at 60, it goes back up also. Air rising at the equator is low pressure. Air sinking at 30 degrees is high. At 30 degrees is high pressure. Now notice that this is named the Hadley cell. There's another cell up here and up here. This is called the polar cell. But that's basically what you need to remember. If I mention Hadley cell, that's what I'm talking about. Is this cell where it goes up at 0 degrees and back down at 30. Again, lots of moisture, very dry. 0 to 30, the winds blow from the east to the west, but they're going to curve. This drives the air and ocean currents in a clockwise. So from 0 to 30, it goes in the clockwise. In the southern hemisphere, it goes counterclockwise. From 30 to 60, air winds goes from the west to the east because it's going faster here than what it is at 60 degrees. It drives the weather patterns in North America. Now, one way to remember that is if you're going on an airplane flight from LA to New York, it's going to take you 4 hours and 47 minutes. Why? Because you have a tailwind. Well, what's going to happen when you're coming back? Well, you've got a headwind, and therefore it's going to take you approximately 30 minutes longer to go the same distance. Now, hopefully that made sense. If not, let's watch this.
If you've ever watched the news during a hurricane or wintertime nor'easter, you've probably noticed that big storms spin over time as they travel. In the northern hemisphere, they spin counterclockwise. But if you were watching a storm in the southern hemisphere, you'd see it spinning clockwise. Why do storms spin in different directions depending on their location? And why do they spin in the first place? A storm's rotation is due to something called the Coriolis Effect, which is a phenomenon that causes fluids like water and air to curve as they travel across or above Earth's surface. Here's the basic idea. Earth is constantly spinning around its axis from west to east. But because Earth is a sphere and wider in the middle, points on the equator are actually spinning faster around the axis than points near the poles. So imagine you were standing in Texas and had a magic paper airplane that could travel hundreds of miles. If you threw your airplane directly northward, you might think it would land straight north, maybe somewhere in Nebraska. But Texas is actually spinning around Earth's axis faster than Nebraska is, because it's closer to the equator. That means that the paper airplane is spinning faster as well, and when you throw it, that spinning momentum is conserved. So if you threw your paper airplane in a straight line toward the north, it would land somewhere to the right of Nebraska, maybe in Delaware. So from your point of view in Texas, the plane would have taken a curved path to the right. The opposite would happen in the southern hemisphere. An object traveling from the equator to the south would get deflected to the left. So what does this have to do with hurricane spinning? Well, at the center of every hurricane is an area of very low pressure. As a result, the high-pressure air surrounding the center, or eye, of a storm is constantly rushing toward the low-pressure void in the middle. But because of the Coriolis effect, the air rushing toward the center is deflected off course. In the northern hemisphere, the volumes of air on all sides of the eye keep getting tugged slightly to the right. The air keeps trying to make its way to the middle and keeps getting deflected, causing the entire system to spin in a counterclockwise direction. In the southern hemisphere, where the Coriolis effect pulls air to the left, the opposite happens. Storms spin around the eye in a clockwise manner.
So, a practice FRQ 4.5. Can you explain how the sun is responsible for the pattern of air circulation seen in cycle C at 0 degrees to 30 degrees? If you want more help with this, there are videos out there that deal with showing what happens if you're on a merry-go-round and throw something from the center to the outside, or from someone at the outside to the opposite side. You might want to look at those. Hopefully this was helpful. Thank you and have a great day.